Magnetars are among the most extreme and enigmatic objects in the cosmos. These neutron stars are born from the explosive death of massive stars in supernovae, leaving behind a core so dense that a single teaspoon of its matter would weigh billions of tons. But what truly sets magnetars apart is their magnetic field, which can be 1,000 times stronger than that of a typical neutron star and up to a quadrillion times stronger than Earth's magnetic field. This makes them the most magnetic objects known in the entire universe. The magnetic field of a hypermagnetic stellar remnant is so powerful it can distort the shape of atoms and rip electrons from atomic nuclei, creating an exotic state of matter. It can affect regions hundreds of kilometers away and has the potential to destroy or rearrange the chemical bonds of anything that comes close. If such an object were located within 1,000 kilometers of Earth, it could wipe the data from every credit card on the planet, and that's still considered a safe distance in cosmic terms. These highly magnetized neutron stars occasionally undergo starquakes, sudden shifts in their rigid crusts due to the immense stress caused by magnetic tension. These events can release massive bursts of high-energy radiation, such as X-rays and gamma rays, outshining entire galaxies for brief moments. In 2004, a giant flare from SGR 1806-20, located about 50,000 light-years away, was so intense it affected Earth's ionosphere and briefly altered our planet's radio communications. It released more energy in 1/10 of a second than the Sun emits in 100,000 years. There are only about 30 confirmed examples of these rare stellar anomalies in our galaxy, though many more are believed to exist undetected. Their lifespans as active ultramagnetized remnants are relatively short, only about 10,000 to 100,000 years, after which their magnetic fields decay and they become indistinguishable from ordinary neutron stars. Theories suggest that these compact titans may form in conditions of extremely fast rotation and intense magnetic dynamos during core collapse supernovae. Some could even be created during neutron star mergers, which are also sources of gravitational waves and heavy elements like gold and platinum. There's also growing speculation that such magnetic objects could be connected to fast radio bursts, FRBs, mysterious, millisecond-long pulses of radio energy detected from across the universe. In 2020, a galactic source known as SGR 1935+2154 was observed emitting an FRB-like signal, offering the strongest evidence yet for a link between these neutron stars and these cosmic radio flashes. Despite their rarity and distance, these exotic pulsars may play a crucial role in shaping galactic ecosystems. Their powerful winds and radiation influence surrounding gas and star formation, and their eruptions may inject high-energy particles into interstellar space. Some researchers even hypothesize that a nearby magnetic eruption from one of these objects could contribute to mass extinctions if one were ever close enough, though thankfully, the known ones are far away. These stellar remnants also challenge the limits of our physics. The extreme conditions near their surfaces offer a natural laboratory for studying quantum electrodynamics in strong magnetic fields, where space itself may behave nonlinearly, and vacuum birefringence, a bizarre effect where light splits into different polarizations, may occur. Because of their extreme properties, these ultradense stars are also candidates for explaining some of the universe's most violent and short-lived transients. Some gamma-ray bursts, specifically the short-duration kind, might originate not from black hole formation, as once thought, but from highly magnetized neutron stars collapsing under their own gravity. In such scenarios, a rapidly spinning object of this type forms briefly and then collapses into a black hole, emitting a final, devastating outburst of energy. These cataclysmic moments, though fleeting, can be detected across billions of light-years. These neutron-born giants are not just destructive forces, they are also cosmic beacons of fundamental physics. Studying their emissions allows astronomers to probe the behavior of matter and energy under conditions that cannot be recreated on Earth. Their surfaces may host nuclear pasta, a bizarre state of matter where atomic nuclei are compressed into shapes resembling spaghetti or lasagna, theorized to exist only in the crusts of neutron stars. These structures are among the strongest materials in the known universe, far more resilient than any terrestrial metal. Another mystery these dense stars present is their periodicity and timing irregularities. Unlike regular pulsars, they often exhibit erratic spin-down rates, glitches, sudden changes in rotation speed, and timing noise. These behaviors hint at complex internal dynamics, possibly involving superfluid interiors or crustal deformations, processes that lie at the frontier of theoretical astrophysics. Despite their intense magnetic fields and compact size, just around 20 kilometers in diameter, these objects can impact entire regions of space. Their magnetospheres are thought to be twisted and dynamic, filled with currents of particles trapped by magnetic loops. These structures can break and reconnect in a process similar to solar flares, but on a vastly more energetic scale. The resulting emissions can include both persistent X-ray luminosity and sudden, giant flares lasting mere seconds but carrying incredible energy. Observationally, these celestial anomalies often appear as anomalous X-ray pulsars, AXPs, or soft gamma repeaters, SGRs. These designations refer to how they were first detected, either through persistent X-ray emissions that don't match expectations from standard pulsars, or through unpredictable bursts of soft gamma rays. Only later did astronomers realize that these seemingly separate classes were likely manifestations of the same underlying phenomenon, magnetic decay in a hypermagnetized neutron star. These hyperactive remnants may also hold clues to the early universe. Some models suggest that the very first stars, population 3 stars, made almost entirely of hydrogen and helium, could have ended their lives in this state, seeding the cosmos with intense fields and contributing to reionization epochs. If so, ancient versions of these stars might still drift through the cosmos, faint and quiet, but once having lit up the early sky with invisible fury. In recent years, these magnetic powerhouses have also become key suspects in some of the strangest astronomical mysteries. Among them are the so-called fast radio bursts, FRBs, powerful, millisecond-long flashes of radio waves coming from distant galaxies. While their origin remained unknown for over a decade, a breakthrough came in April 2020 when an FRB-like signal was traced to a known galactic neutron star, SGR 1935+2154. Although this event was far weaker than extragalactic FRBs, it was the first time such a burst was observed from within our galaxy, suggesting that at least some FRBs may be powered by magnetic activity, possibly through sudden magnetic reconnection events or crustal fracturing. These rotating anomalies also show us how fragile our technological society is in the face of cosmic forces. A flare aimed directly at Earth could damage satellites, disrupt communications, and even affect power grids. While the chances are extremely low, the potential for such events, called cosmic EMPs, adds a fascinating and humbling layer to our understanding of space weather hazards. In fact, some scientists speculate that a burst from one of these stellar objects could, in theory, be mistaken for a nuclear detonation in orbit due to its intense gamma and X-ray output. Beyond their destructive possibilities, these compact dynamos are deeply valuable to fundamental science. Their surfaces and interiors push physics beyond the standard model, into regimes of superfluidity, superconductivity, and quantum plasma behavior. The intense magnetic fields may even warp the vacuum of space, causing light itself to behave differently, a prediction of quantum electrodynamics, QED, known as vacuum birefringence, which astronomers are now attempting to detect observationally in the polarized light emitted by these stars. Some researchers have proposed even more exotic ideas involving these ultramagnetic phenomena. For instance, it's been suggested that when two of them merge, they could produce not only gravitational waves detectable by instruments like LIGO and Virgo but also rare types of kilonovae, brilliant explosions that forge heavy elements like uranium and gold. These events may even outshine supernovae and briefly rival the brightness of an entire galaxy. Others hypothesize that these high-field neutron stars may occasionally become blitzars, a theoretical class of objects where a rapidly rotating star remains stable only temporarily before collapsing into a black hole once it slows down. This collapse could produce a final radio burst, offering a possible origin for one-time FRBs. If such objects exist, they represent some of the shortest-lived and most extreme transitions in astrophysical evolution. Even more speculative are the ideas that these compact beacons could be used as natural probes to detect dark matter. Certain models suggest that dark matter particles might accumulate in neutron stars and influence their temperature or magnetic activity. Since these cosmic engines are already extreme in their emissions, small changes could stand out more clearly, making them potential laboratories for testing these elusive theories. In the search for dark matter, these high-energy sources provide a unique environment where the density and energy are so extreme that exotic particles, such as axions or sterile neutrinos, might interact more noticeably than in other settings. Some models predict that axions, if they exist, could be produced in the dense cores of such stars and convert into X-ray photons in their intense magnetic fields. Detecting such signals could be a revolutionary step toward confirming new physics beyond the standard model. The birth of such a star itself remains a deeply fascinating process. In the aftermath of a core collapse supernova, if conditions are right, especially a combination of extremely rapid rotation and massive core mass, a magnetic dynamo effect can amplify seed magnetic fields to unimaginable strengths. This process happens within milliseconds, creating a stellar object with a field strong enough to store energy equivalent to the total luminosity of the Sun over 10 million years. That energy is slowly released over thousands of years through radiation, bursts, and violent starquakes. These neutron star variants are also linked to some of the most peculiar supernova remnants. These remnants often display asymmetries, high-energy emissions, and odd morphologies that may be shaped by the newborn object's outflows and rotation. In rare cases, the compact remnant itself might power a type of superluminous supernova, outshining standard explosions by factors of 10 or more. These events are so bright they can be seen in distant galaxies, acting like cosmic lighthouses that tell us about the deaths of the most massive stars. As our instruments improve, especially with next-generation telescopes like the James Webb Space Telescope, the Extremely Large Telescope, and upcoming high-energy missions, we are poised to study these hypermagnetic neutron stars across a wider range of wavelengths, including infrared and gamma-ray spectra. This will help us uncover dormant or hidden stellar anomalies cloaked within thick nebulae or in distant galaxies, extending our understanding of how often they form and how they influence their environments. Even now, astronomers are developing new techniques to detect the subtle polarization patterns in the light emitted by these exotic remnants, which could offer the first direct observational proof of quantum vacuum effects. If confirmed, this would not only validate long-standing predictions in quantum field theory but also mark the beginning of using neutron stars as astrophysical laboratories for high-energy physics. Despite their rarity, these magnetic titans exert an outsized influence on our understanding of stellar death, quantum physics, cosmic evolution, and even potential threats to technological civilizations. They are cosmic paradoxes, born in violence, fueled by decay, capable of both destruction and discovery. Their bursts echo across time and space, carrying with them the secrets of matter, magnetism, and the most extreme states nature can offer. And so, in the vast silence of space, these compact powerhouses pulse like cosmic heartbeats, rare, erratic, and impossibly intense. They are the ticking time bombs of the stellar graveyard, their magnetic fields so immense they seem to tear at the very fabric of reality. Each flare, each quake, each ghostly radio flash that reaches us is a message from a realm where matter is crushed, space is twisted, and physics dances on the edge of the unknown. They remind us that the universe is not just a place of serene beauty and gentle starlight. It is also a domain of chaos and power, of entities that bend light, warp atoms, and silence entire regions of space with a single burst. These magnetic beacons are among the loudest voices in this cosmic chorus, speaking in the language of X-rays, gamma rays, and trembling magnetic storms. And yet, for all their power, they are fragile, lasting only a fleeting moment on the timeline of the universe. A few thousand years of magnetic wrath, a few violent outbursts that illuminate the cosmos, and then they fall silent, fading into the dark as ordinary neutron stars, their fury spent, their identity erased. Perhaps, one day, we will witness the birth of one in real time, a titanic supernova flashing through a distant galaxy, followed by a newborn star whose magnetic scream echoes across the void. Until then, we search the skies for their signs, for the tremors in spacetime, for the brief flashes in radio and gamma light, for the silent warnings that something ancient and violent still stirs in the deep. In the end, these stellar enigmas are not just stars. They are cosmic relics of catastrophic transformation, monuments to the extremes of matter and energy. They challenge our models, fuel our theories, and inspire awe in every scientist who dares to study them. To look at one is to peer into the limits of nature, to glimpse a world where gravity, magnetism, and quantum mechanics collide in a symphony of destruction and insight. And that, perhaps, is their greatest power, not just to burn, but to illuminate. The future of high-field neutron star research promises to be just as electrifying as the objects themselves. As new detectors come online, like the Square Kilometre Array, SKA, the Enhanced LIGO-Virgo-Cagra Gravitational Wave Network, and advanced X-ray observatories such as Athena, we will be able to detect more subtle signals, fainter bursts, and earlier activity across the cosmos. These tools will not only find more of these elusive stars but may allow us to catch their birth moments, track their magnetic decay in real time, and measure their influence on nearby cosmic structures with unprecedented precision. One of the most exciting frontiers is multi-messenger astronomy, the coordinated study of cosmic phenomena through different signals, light, gravitational waves, neutrinos, and cosmic rays. These ultramagnetized objects stand at the intersection of many of these domains. A single flare might emit not just X-rays and radio bursts but also gravitational ripples or bursts of high-energy neutrinos. Detecting all these messengers from one event would provide an unparalleled window into the extreme physics near the surface of such an object. Scientists also speculate about more speculative outcomes of behavior from these extreme remnants, such as their role in potentially powering jets from newborn black holes or forming the mysterious central engines behind superluminous transients. These ideas are still being tested, but if confirmed, these stars could prove central to some of the brightest, strangest explosions in the universe. There is also philosophical weight in their study. These ultradense, magnetic survivors compress mass, energy, and force into a volume smaller than a city, yet their outbursts are felt across galaxies. They embody contrast, the dead cores of stars, yet furiously active, ancient relics of stellar collapse, yet capable of shaping cosmic evolution. They challenge the notion that the universe is passive or predictable. In a cosmos governed by order, they are wild cards, reminders of cosmic volatility. Even the word itself, magnetar, carries a sense of myth and menace. It suggests something that is not merely a star but an elemental force, something that refuses to fade quietly into the night. They are not here to shine gently like the sun, but to explode, fracture, pulse, and vanish. Their lives are not measured in billions of years but in bursts and collapses, in sudden ruptures of energy and silence. These extraordinary pulsars also invite us to dream bigger. They push the limits of our understanding of nuclear matter, of field theory, of time, of structure. They force us to ask new questions. How strong can a magnetic field truly be? What lies beyond the quantum horizon of such stars? What happens when one dies, not as a neutron star, but as something stranger, an exotic object yet unnamed? And what might they tell us about ourselves? About the fragility of our world in the face of cosmic forces, and yet our ability, through intellect and curiosity, to detect, study, and even predict the behavior of such cataclysmic entities. These magnetic anomalies also raise profound questions about the stability of matter itself. At their cores, densities exceed that of atomic nuclei, and quantum degeneracy pressure is pushed to its limits. Some theories suggest that deep inside such stars, matter might transition into a state of quark-gluon plasma, where neutrons break apart into their constituent quarks. If true, these objects could be transitional, halfway points between neutron stars and hypothetical quark stars or even strange matter stars, exotic phases of matter that have never been observed directly but could redefine our understanding of what constitutes a stable atomic nucleus. Their magnetic fields are not only strong but incredibly dynamic. These fields evolve rapidly compared to ordinary stars, undergoing decay and restructuring over timescales of just thousands of years. This magnetic evolution can twist the crust, drive seismic activity, and power the bizarre emissions we detect from Earth. Some of these stars exhibit persistent X-ray luminosity millions of times greater than what could be explained by their cooling alone, suggesting that magnetic field decay is continuously heating the surface and deeper layers of the star. What's especially fascinating is the way these magnetic fields interact with space itself. In fields as intense as those near such an object's surface, up to 10 superscript 1 Gauss, quantum electrodynamics, QED, predicts that even the vacuum behaves differently. Under such stress, empty space becomes polarized, meaning it acts like a medium that can bend or alter light. This phenomenon, known as vacuum birefringence, has been theorized since the 1930s but has only recently begun to be tested using the polarized light from distant neutron stars. These environments are ideal laboratories for such tests, and they may help us observe quantum effects on a cosmic scale. These stars also offer potential clues about the early universe. If the first generations of massive stars, composed of nearly pure hydrogen and helium, formed ultramagnetic remnants at the end of their lives, those early cosmic lighthouses might have influenced the reionization epoch, when ultraviolet radiation from the first luminous sources ionized the intergalactic medium. Though no ancient examples have yet been detected, their fingerprints may be hidden in the structure of early galaxies or in the diffuse gamma-ray background. Even the crusts of these extreme objects defy intuition. Composed of ultradense nuclear matter, the crust may host what physicists call nuclear pasta, phases of matter with shapes like rods, slabs, and spirals, caused by the strange interplay of nuclear forces and gravity. These forms are stronger than any material known, and they may determine how and when such crusts crack under pressure, triggering powerful starquakes that release enormous energy in an instant. These quakes can also trigger magnetic reconnection events, similar to what happens during solar flares but magnitudes more powerful. The twisted magnetic field lines suddenly snap and reconfigure, converting magnetic energy into radiation and particle acceleration. This is believed to be the source of the rare but terrifying giant flares observed in just a few of these neutron stars, events that are visible across galaxies and have been known to temporarily disrupt satellites on Earth. Despite all of this, these cosmic enigmas remain shrouded in mystery. Their rarity, unpredictability, and short active lifetimes make them difficult to study. We only catch them in moments of violent activity, through a sudden flare or a burst of radio emission. But these glimpses are enough to hint at a realm of physics beyond the edge of what we know. Some of the most speculative and thrilling ideas surrounding these objects stretch into the realm of theoretical physics and cosmology. Because they reach energy densities and magnetic fields far beyond what can be produced in any Earth-based experiment, some researchers have proposed that they may act as natural portals into high-energy regimes where the standard model of physics begins to break down, potentially revealing hints of new fundamental forces or extra dimensions. One such idea involves the potential interaction between these hypermagnetized stars and dark energy. Though purely hypothetical, some physicists have explored whether the decay of ultra-strong magnetic fields in a dense, compact object could be influenced by the same mysterious force that drives the accelerated expansion of the universe. While no observational evidence yet supports this, it reflects the way these stars invite connections between the small-scale structure of matter and the large-scale structure of spacetime. Another bold hypothesis is that ultramagnetic neutron stars could trigger localized violations of Lorentz invariance, one of the foundational principles of relativity. In regions where magnetic fields are so intense that virtual particles become real, space itself may behave differently, slowing or warping the propagation of light, altering the polarization of vacuum fluctuations, and even affecting the Casimir effect at extreme scales. These effects, if ever observed, would indicate that the laws of physics may not be truly uniform across the universe. Even more intriguing are the quantum gravity models that suggest that the interiors of these compact stellar anomalies might contain cores of Planck-scale matter, regions where quantum effects of gravity itself become significant. These models venture into the territory of loop quantum gravity or string theory, where the fabric of space and time is discrete, and where such stars might serve as observable examples of quantum spacetime phenomena. Some theorists also link these highly magnetized remnants to the early conditions of black hole formation, speculating that extremely massive versions could briefly exist in a state of near collapse before transitioning into black holes. This raises the possibility of observing one of these objects in its final moments, just before the event horizon forms, offering a rare opportunity to study physics on the threshold between neutron stars and black holes. If such a collapse occurs asymmetrically, it could also generate gravitational wave signatures, distinct from binary mergers, and potentially observable by future detectors like LISA or the Einstein telescope. These exotic pulsars also might be responsible for the most powerful explosions in the universe, superluminous supernovae and long-duration gamma-ray bursts. In these events, a rapidly rotating, newly formed magnetic star injects energy into the supernova ejecta through its intense magnetic dipole radiation, making the explosion many times brighter than normal. This magnetar-powered supernova model is increasingly favored to explain extremely luminous transients observed in distant galaxies, which would otherwise require unphysical amounts of radioactive nickel. And finally, there's the ongoing question of their connection to extraterrestrial signals. While it's firmly in the speculative zone, a small but persistent community of scientists entertains the idea that highly regular or unusual emissions from such stars, particularly repeating FRBs with structured patterns, could one day point to astrophysical phenomena that mimic or mask artificial signals. This isn't to suggest that these objects are alien technology, but rather that their physics is so strange, so rare, and so extreme that we must be careful not to misinterpret what we observe. Ultimately, these ultradense entities are like messages from the edge of physical law. Each burst, each flare, each unexpected twist in their behavior reveals not just something about stars, but about the universe itself, its extremes, its origins, and perhaps even its fate. As we look ahead, the future of high-field neutron star science is poised to enter a golden era, driven by the convergence of multi-messenger astronomy, machine learning, and next-generation observatories. Instruments currently under development will make it possible to detect and analyze these exotic remnants with an unprecedented level of detail, helping to solve some of the deepest astrophysical puzzles of our time. The upcoming Athena, Advanced Telescope for High-Energy Astrophysics, mission by the European Space Agency is designed specifically to observe high-energy phenomena like these magnetic titans. With far greater sensitivity than current X-ray telescopes, Athena will be able to track faint emissions from dormant or newly formed remnants, explore their crustal temperatures, and map their magnetic topologies in 3 dimensions. This could help confirm the presence of nuclear pasta structures or even detect starquake precursors, warning of imminent flares. At the same time, the Square Kilometre Array, SKA, a massive international radio telescope project, will be able to detect thousands of new neutron stars, including many previously hidden magnetic anomalies. Its ability to monitor wide swaths of sky with high temporal resolution will allow it to catch fast radio bursts in real time, potentially correlating them with activity in distant galaxies. This could establish a solid statistical link between FRBs and these compact powerhouses, or uncover multiple mechanisms behind these mysterious events. In parallel, gravitational wave observatories like LIGO, Virgo, CAGRA, and the future Einstein telescope are preparing to detect more subtle signals than ever before. While starquakes or crustal oscillations might produce weaker gravitational waves than binary mergers, the cumulative improvements in sensitivity could finally bring these whispers of stellar violence into the range of detection. The identification of a gravitational wave associated with a magnetic flare would be a landmark discovery, linking surface activity to spacetime ripples. There is also growing interest in building space-based gamma-ray detectors capable of catching high-energy bursts at millisecond resolution, such as Theseus, Transient High-Energy Sky and Early Universe Surveyor. These instruments will allow us to observe giant flares from ultramagnetized neutron stars in other galaxies and explore whether such events could be the origin of a subset of short or intermediate gamma-ray bursts. Researchers are also experimenting with machine learning algorithms to scan archival data for missed signals, low-level or short-lived emissions that could correspond to previously unknown magnetic activity. This data mining approach is beginning to pay off, revealing candidates that might have gone unnoticed in earlier surveys. Combined with new data streams, AI may help classify these stellar remnants into distinct families based on their flare patterns, spin behavior, or evolutionary history. As our toolbox expands, so too does the ambition. Some astrophysicists dream of creating detailed magnetohydrodynamic simulations of magnetic neutron stars from birth to decay, capturing not only the internal particle dynamics but also how their fields evolve, how they interact with surrounding nebulae, and how their emissions affect the interstellar medium over thousands of years. These simulations could become predictive, helping observatories anticipate when and where to expect flares or outbursts. Even further into the future, there are proposals for X-ray interferometers in space, telescopes capable of resolving the surfaces of neutron stars directly, much like how optical interferometers now image distant exoplanets. If realized, we could one day see the hotspots, cracks, or oscillations on the crust of one of these magnetic relics with our own eyes, in real time. But perhaps most exciting is the unknown. Every time we look closer at these stellar puzzles, we uncover something that defies expectations, a pulse that shouldn't exist, a flare that exceeds theoretical limits, a radio burst from a supposedly dead star. These anomalies are not errors, they are invitations. These objects teach us that the universe is not only more extreme than we imagined, it's stranger than we can imagine. They don't just challenge our understanding of physics, they reshape our relationship with the cosmos itself. In many ways, they are the ultimate expression of cosmic tension, the gravitational collapse of a giant star balanced precariously by quantum pressure and an unleashed magnetic fury. Their existence reveals how the universe stores vast energies in invisible forms, then releases them in sudden, breathtaking moments of transformation. From a philosophical perspective, these dense cosmic bodies raise profound questions about the thresholds of nature. They force us to ask, how far can you push matter before it breaks? How much energy can be locked into a magnetic field before it snaps and floods the cosmos with radiation? What are the ultimate limits of visibility, of time, of energy, of silence, if silence can be shattered by a burst of gamma rays traveling 50,000 light-years only to ping our instruments for a fraction of a second? And what does it mean that such forces are out there, silently evolving, flaring, and collapsing, long before life emerged on Earth, and likely long after it ends? These remnants of stellar collapse are both messengers and monuments, fossils of death throes but also active engines of change in the galactic ecosystem. Their flares can ionize interstellar gas, compress molecular clouds, and potentially trigger new waves of star formation, linking death to rebirth on cosmic timescales. Their danger potential is not science fiction, it's a subtle but real reminder that space is not benign. A sufficiently close flare from a hypermagnetic neutron star could, in theory, strip away a planet's ozone layer, bathe it in high-energy radiation, and alter its biosphere permanently. Some researchers have even speculated that past extinction events on Earth could have been triggered not by supernovae alone, but by distant emissions from one of these stellar anomalies, invisible to ancient skies yet devastating to the chemistry of the atmosphere. This leads into a deeper cosmological role. Ultramagnetized stellar corpses may serve as filters of habitability. In densely populated star-forming regions or early galaxies, their presence might sterilize or disrupt planets in nearby systems. If these exotic remnants were more common in certain epochs of galactic evolution, they could delay or reduce the emergence of life, acting as temporal gatekeepers. Conversely, the decay of their fields could enrich the interstellar medium with particles and radiation needed for complex chemistry. They are, in a sense, both destroyers and midwives. These magnetic giants also speak to the asymmetry of time. They are born in seconds but take tens of thousands of years to cool, fade, and transform. Their bursts occur in milliseconds, yet the energy travels across space for millions of years. We are catching echoes of ancient violence, fossil explosions that speak not just of stellar collapse, but of the arrow of time itself, encoded in magnetic entropy and neutron-rich decay. Some researchers now explore how the remnants of such stars, those that have quieted, spun down, and faded, might still influence the galactic magnetic field on large scales. These silent neutron star variants could serve as seeds or anchors for the sprawling magnetic architecture of the Milky Way, subtly guiding the dynamics of cosmic rays and the behavior of interstellar gas over kiloparsec distances. In a way, these rare cosmic engines are like punctuation marks, powerful, transformative, unexpected. They break the smooth narrative of space with sudden, chaotic interjections, rewriting the structure around them. And we, fragile observers from a safe distance, learn not only from their light, but from their silences, the long periods between eruptions, the quiet decay of their fields, the slowly dying heartbeat of their spin. In the future, as we probe deeper into the quantum structure of space, the composition of dark matter, and the origins of high-energy cosmic phenomena, these magnetic powerhouses may not remain on the periphery, they may become central to our theories of everything. As our understanding deepens, these compact objects may ultimately act as bridges, linking disparate domains of knowledge across astrophysics, quantum field theory, cosmology, and even philosophy. They're not just exotic neutron stars, they are a testbed for ideas that stretch from the infinitesimal to the infinite. In their tortured cores and violent eruptions, they encode the interplay of gravity, electromagnetism, nuclear forces, and quantum mechanics, four of the fundamental pillars of physical reality. More than any other known object, these stellar enigmas allow us to ask questions like, what happens to quantum fields under the strongest known magnetic stress? Can spacetime itself become magnetized? Do particle masses or charges shift in such intense conditions? Can light cease to behave like light under pressure from warped magnetic vacuums? These aren't idle musings, they are now the subject of peer-reviewed studies. Theoretical physicists are actively using these remnants to probe QED in curved spacetime, the behavior of axion-like particles, and the possible symmetry breaking at extreme energies. It's conceivable that these high-field stars might even serve as indirect detectors for phenomena beyond the standard model, not because they reveal them directly, but because their behavior deviates in ways that hint at something deeper underneath. On the observational side, these ultramagnetic anomalies may be used as natural detectors of gravitational waves in unconventional ways. For example, when their crusts crack or rearrange due to magnetic stress, they send ripples through their dense interiors. These internal vibrations could couple with spacetime, creating faint gravitational echoes. If we can detect these signals, we may gain a kind of seismograph of ultradense nuclear matter, mapping the hidden interiors of collapsed stars. Then there's the question of cosmic memory. These neutron-born relics form from the deaths of massive stars, which formed from clouds enriched by earlier supernovae. Those clouds, in turn, may have been compressed by the shock waves of even older stellar deaths. Thus, a single magnetic beacon holds within it the fingerprints of many past generations of cosmic evolution. Its spin, temperature, and magnetic profile encode a history of pressure, rotation, fusion, collapse, and chaos that goes back billions of years. Studying it is like reading the fossil record of matter itself. And yet, for all their violence and extremity, there is something strangely elegant about these entities. Their spin-down is predictable. Their magnetic decay follows statistical patterns. Their flares can be described with equations, their behavior reproduced in simulations. This juxtaposition, raw power wrapped in mathematical grace, is what makes them so fascinating to scientists and artists alike. Even in science fiction and speculative thought, these stars have become symbols of ultimate energy, cosmic danger, or hidden intelligence. Some authors imagine them as galactic defense systems, deliberately engineered to sterilize regions of space. Others depict alien civilizations harnessing their magnetic fields as interstellar power sources or communication beacons. These stories, while fictional, stem from real scientific awe. These compact titans are so powerful that they blur the line between natural phenomenon and deliberate design. We are still just beginning to scratch the surface of what these cosmic riddles can teach us. Every new detection opens more questions than it answers. Every unexpected burst, every strange spin glitch, every unusually dim or bright flare defies neat categorization. They are stellar puzzles, burning themselves into spacetime, waiting for the right minds, and the right tools, to decipher them. And perhaps that's the most exciting truth of all, in the silence between bursts, in the darkness between detections, these beacons of magnetic fury are still watching. Still spinning. Still waiting to be understood. As we venture deeper into this century of cosmic discovery, these stellar phenomena stand like beacons at the edge of comprehension, reminding us that the universe is still wild, still full of surprises, still more powerful and strange than our instruments alone can measure. They are not remnants of stellar collapse alone, they are the echoes of the universe testing its own limits. In the next decades, new missions and technologies may bring us even closer. Constellation-class X-ray observatories, deep learning-enhanced all-sky monitors, space-based radio arrays, and ultra-sensitive polarization detectors could transform our ability to catch the earliest signals of a magnetic neutron star's life, and its final breath. We may even discover entirely new classes of transient behavior, from slow-burn flares to silent neutrino emissions, reshaping our models of how matter behaves under strain. Some theorists go even further, proposing that these hypermagnetic remnants could represent a phase transition point in stellar evolution, not just an endpoint. In these scenarios, what we call a magnetized neutron star is a temporary state of matter undergoing transformation, and what comes next may lie outside the taxonomy of stars entirely. The possibility that such an object could shed its magnetism violently and transition into a black hole or an exotic compact object opens the door to a new kind of cosmic life cycle, one we have never seen, but may detect through its afterglow or gravitational memory. In a broader cosmological context, these extreme stellar remnants also serve as standardizable energetic beacons. Some researchers are exploring whether the energy profiles of their giant flares could be used as standard candles, much like Type Ia supernovae, to measure distances across the universe. If this proves feasible, these magnetic powerhouses could become new tools in cosmology, helping us map dark energy and cosmic acceleration from another angle. And we cannot ignore their metaphorical resonance. In educational outreach, art, literature, and media, these neutron star beacons offer a vivid symbol: the invisible made visible, the silent made deafening, the dead made violently alive. A star that dies but refuses to go quietly, screaming across the galaxy with one final, magnetic roar. They echo the nature of knowledge itself. What is such a star, if not a mystery waiting to burst open? A locked vault of cosmic history, cracked open by spin and stress. A riddle, not written in words, but in light and gravity and time. In the same way we once feared comets and now land probes upon them, in the same way we once wondered at stars and now build models of their fusion cores, ultramagnetized neutron stars represent our next frontier, not in distance, but in intensity. A test of our ability to see, to measure, to understand what was once considered too violent, too brief, or too rare to matter. Yet they do matter, profoundly. Because they prove that even after death, a star can still shape galaxies. Even in silence, it can still speak. Even in darkness, it can still burn. And somewhere, far beyond the reach of our telescopes, a newborn magnetic anomaly may be spinning now, winding its field tighter with every millisecond, building toward a flare that will one day ripple across space, pass silently through frozen nebulae, slip past ancient stars, and arrive, uninvited but undeniable, at Earth. And when it does, we will listen. And when we listen, truly listen, with detectors tuned to the faintest crackle of X-rays, the quickest flash of radio light, the most fleeting twist in polarization, we do more than receive data. We witness. We become part of the long chain of cosmic awareness, stretching from the first atoms that cooled into stars, to the minds that now wonder what lies beyond them. Because every one of these hypermagnetic remnants is a paradox, a corpse that pulses, a death that flares with life. It is what remains when a star's core has collapsed, but something, spin, charge, field, refuses to yield. Refuses to be quiet. Refuses to vanish. And we must ask, why? Perhaps it is because the universe, in its deepest layers, stores energy like memory. Perhaps the rotational fury of a dying star is not simply a mechanical residue, but a record of how that star lived, how fast it turned, how deep it fused, how violently it died. And the magnetic field? A scar. A signature. A branding of space itself, saying I was here. I burned once. I changed the sky. It is this defiance of erasure that makes these neutron star anomalies so compelling. They are not the ghosts of stars. They are their final voices. And when they erupt, the entire universe becomes their stage. Imagine, billions of years from now, when the cosmos is colder, quieter, emptier. Most stars will have burned out. Galaxies will have drifted too far to see. Black holes may begin to evaporate. And yet, somewhere in that quiet, a dormant stellar relic might still be spinning, slow, cracked, ancient. One last quake, one final flare, and a ripple of energy will expand into the emptiness, a last light in a dying universe. That is the legacy of these magnetic beacons. Not just in their power, but in their persistence. Not in their brightness, but in their timing. Not in their chaos, but in their refusal to be forgotten. They are cosmic storytellers, and their stories are written in fields stronger than imagination, in bursts faster than thought, in radiation older than memory. They teach us that the most extreme forces do not erase the universe, they write it. And as we continue to search the sky, for answers, for signals, for understanding, we realize that these stellar phenomena are not only phenomena to be studied. They are questions incarnate. They are windows through which we glimpse the raw machinery of existence. And they are reminders that even in the death of stars, there is something fiercely alive. So what, then, is such a remnant? It is not merely a collapsed star, nor just a scientific classification on an astrophysical chart. It is a threshold, a limit state of matter and light, a screaming point in the universe where the rules begin to blur, and new laws begin to whisper. It is the moment where extremes become clarity. Where mass becomes motion, and motion becomes fire, and fire becomes memory. These cosmic engines remind us that the cosmos is not sterile. It is not calm. It is a place of tension and release, of structures that shatter and reform, of silence broken by brilliance. Their lives are not measured in warmth or longevity, like stars that shine for billions of years. Their legacy is not in comfort, but in impact. They live in milliseconds of fury. In quakes that twist their steel-like crusts. In magnetic screams that stretch across galaxies, carried on rays invisible to our eyes, but deadly in their power. To understand one of these high-energy corpses is to touch the edge of physics. It is to glimpse what matter becomes when gravity squeezes and time warps and magnetism devours the sky. It is to stare into the cold heart of a dead star and see motion, memory, magnitude. And still, they spin. Long after their flares fade, long after the X-rays quiet, long after their names are forgotten in catalogs and missions and data sets, they spin. In darkness, they whisper. In silence, they wait. In emptiness, they endure. Because the universe is not just expansion, it is remembrance. Not just stars that are born, but forces that refuse to die quietly. Not just beauty, but fury. Not just light, but magnetism woven into the very geometry of space. And if one day we understand the final structure of everything, matter, time, consciousness, it may be because we first listened to the irregular pulse of a neutron star with a magnetic heart across the vacuum. We watched the star quakes, counted the decaying spins, traced the echoes of energy that came from some forgotten corner of the sky, where a star collapsed and then refused to fade. So let this be the closing message: these stellar titans are not dead stars. They are still speaking. And they are still being heard.